Dear students, welcome. This is our second class on vector calculus. Let us continue. Derivative of a function of a function. Derivative of a function of a function. Derivative of a function of a function. Suppose that R vector. Suppose R vector be a vector function of the scalar variable. Suppose that R vector is a vector function of the scalar variable S. Also suppose that S is a scalar function of another scalar variable t. Then R vector is a vector function of the scalar variable t. An increment delta t in t produces an increment delta s in s and an increment delta r by in r. Also, when delta t tends to 0, then delta s tends to 0 and delta r vector also tends to 0. Now, from definition, dr vector by dt equal to limit as delta t tends to 0, delta t. Delta r vector by delta t. This is equal to limit delta t tends to 0, delta r vector by delta s by delta t. You may write like this. And by the property of limit, you may write in this way. Delta s. You may write in this way. You may write here delta s. Limit delta t tends to 0, delta s by delta t. Here you may write delta s tends to 0 as delta t tends to 0. From this you may write it is nothing but dr vector by ds and it is ds by dt. Thus, dr vector by dt, this is equal to dr vector by ds by dt. Also, ds by dt can be written in this way. Dr vector by dt. You may write like this also. You should notice that this is a scalar quantity. It is a vector quantity. It is the product of a scalar and a vector. Now, let us discuss about some theorems. Let us discuss about some theorem. Theorem number one. The necessary and sufficient condition and the sufficient condition. The necessary and sufficient condition that a vector function function. A vector t means of the scalar variable t to be constant. Constant is that dA vector by dt equal to 0. This means the vector is independent of t. A vector should be a vector is a constant vector if dA vector by dt this is equal to 0. Necessary condition. The necessary condition. Let us suppose that this vector is a constant vector, constant vector function. Let us suppose that this vector is a constant vector function. Therefore, a vector this is equal to a vector t. Now, dA vector by dt equal to limit as delta t tends to 0 t plus delta t minus a vector t by delta t. This is equal to limit as delta t tends to 0. This is obviously 0 vector divided by dt equal to 0 vector. You may write here it is a 0 vector because a vector is 0, its differentiation will come in vector form. Therefore, it is 0 vector. The necessary condition is very easy. If the vector is a constant vector function, then it is obvious that dA vector by dt equal to 0. Sufficient condition. Sufficient condition means, conversely, suppose that dA vector by dt equal to 0 vector, then we have to show that the vector is a constant vector function. Sufficient condition. Sufficient condition. Conversely, suppose that dA vector by dt equal to 0. We have to show that equal to 0. We have to show that a vector t is a constant vector function. Constant vector function. Let a vector t, you may write it here a1t I cap plus a2t j cap plus a3t k cap. You may write like this. This means dA vector by dt equal to, I have already given you this dA2 by dt j cap plus dA3 by dt k cap. Mind that a1, a2, a3 are scalars. Now, dA vector by dt equal to 0 vector means dA1 by dt I cap plus dA2 by dt j cap plus dA3 by dt k cap equal to 0 vector. This can be written as 0 I cap, 0 j cap plus 0 k cap. You can write in this way also. Now, equating the coefficients of I cap, j cap, k cap, we get equating the coefficients of I cap, j cap, k cap, we get dA1 by dt equal to 0, dA2 by dt equal to 0, dA3 by dt equal to 0. This means A1, A2, A3 are constant scalars. A1, A2, A3 are independent of T. This means that A1, A2, A3 are constant scalars. This means A1, A2, A3 are independent of the variable T, scalar variable T. That is, you may write A1, A2, A3 are scalars which are independent of T. Which are independent of T. Therefore, from this, these are independent of T. Therefore, this is also independent of T. Therefore, dA vector by dt from this, you may write, is also independent of T. Independent of T. This means dA vector by dt independent of T means, this means A vector T is a constant vector function. Vector function is a constant vector function, right? It is very easy. We have given the theorem number 1. Just note it down. It's a very easy theory. I am going to give you 6 theorem. One theorem has been given to you. Theorem number 2. If A vector is a vector function of the scalar variable T, is a vector function of the scalar variable T such that, and the magnitude of A vector is small a, that is, the magnitude of this vector is equal to A. Suppose this. Then number 1. Then number 1, d dt of A vector square should be equal to twice A dA dt. And number 2, A vector dot dA vector by dt. This is equal to A dA by dt. That's very simple. A dA by dt. Very simple. Now, solution. Given that the magnitude of the vector is equal to A, it is not given to be constant. It is the magnitude of the vector A is equal to A. This is given. Now, A vector dot A vector equal to the magnitude of this vector into cos angle between the two vectors is 0. This is equal to A into A. Cos 0 means 1 equal to A square. This can be written as A vector square. Thus, A vector square equal to A square. It is scalar. This means d dt of A vector square, this can be written as d dt of A square. You may write like this, A square. What is this? Since a square is constant, therefore you may write twice a dA dt. Twice a dA dt. Therefore, d dt of a vector square is equal to twice a dA dt. Proved. Thus, d dt of a vector square, this is equal to twice a dA dt. Now number 2. To prove number 2, we have a vector square. This is equal to a square. We have a vector square equal to a square. This means d dt of a vector square, this is equal to d dt of a square. This means d dt of a vector dot a vector, this is equal to, you may write here twice a dA dt. You may write here twice a dA dt. Let me write like this. Means from this step, a vector dot dA vector by dt plus dA vector by dt dot a vector. You may write like this. This is equal to twice a dA dt. This means twice a vector dot dA vector by dt equal to twice a dA dt. Since a vector dot dA vector by dt, this is equal to dA vector by dt dot a vector. Dot a vector. This means a vector dot dA vector by dt equal to a dA dt. Proved. We have proved number 2. We have proved 2 theorems on vector calculus this today. It is very easy. Now, number 3. We are going to give you the theorem number 3. Theorem number 3. Theorem number 3. If a vector is a vector function of the scalar variable t, such that the magnitude of A is constant, such that the magnitude of A is constant. That is, you may write a vector has a constant length. Constant length. In other words, you may write in this way. That is, a vector has a constant length. Means the magnitude of a vector is constant. Magnitude of a vector is constant. Then a vector is perpendicular to dA vector by dt, provided dA vector by dt is not equal to 0. Magnitude of the dA vector by dt is not equal to 0. This is the theory. What is the theory? A vector is a vector function of the scalar variable t, number 1, and it is of constant length. Means the magnitude of the vector A is constant. It is of constant length, means magnitude of the vector is constant. Magnitude of the vector is constant. Also, then we have to show that if the magnitude of dA vector by dt is not equal to 0, then A must be perpendicular to dA vector by dt. A must be perpendicular to dA vector by dt. Must be perpendicular to dA vector by dt. Now, the proof, I am going to give you the proof. What is given? A vector is a vector function of the scalar variable t. Also, magnitude of the vector A is constant. Let us suppose that magnitude of the vector equal to A equal to constant. It is constant given. Magnitude of the vector is constant. It is given. This is equal to the constant. Let us suppose that the magnitude of the vector is. It stands for the magnitude of the vector. A vector, this stands for the magnitude of the vector. Of the vector A. It stands for the magnitude of the vector A. This is constant. Now, A vector dot A vector. This will be equal to the magnitude of this vector, cos 0. You may write like this. This is equal to A1 equal to A square. Since A is constant, this is equal to constant. This means A vector dot A vector equal to constant. This is equal to constant. Notice that the dot product of two vectors. Notice that the dot product of two vectors will be a scalar quantity. And cross product of two vectors is a vector quantity. This means d dt of A vector dot A vector. This is equal to d dt of constant. This means A vector dot dA vector by dt plus dA vector by dt dot A vector equal to 0. On the differentiation of a constant scalar is equal to 0. This is equal to 0. This means 2 times of A vector dot dA vector by dt equal to 0. Since A vector dot dA vector by dt, this is equal to dA vector by dt dot A vector. This means A vector dot dA vector by dt equal to 0. This means, what does it mean? Either A vector is equal to 0 but it is of constant length, or dA vector by dt, the magnitude of this vector is equal to 0. And the third provision is that since the dot product is 0, A vector must be perpendicular to dA vector by dt. Three possibilities are there. Either A vector, the magnitude of the A vector is equal to 0, dA vector by dt modulus of this is equal to 0, or A vector must be perpendicular to this because the dot product is equal to 0. Three possibilities are there. Therefore, A vector equal to 0 or dA vector by dt, this is equal to 0, or A vector is perpendicular to dA vector by dt. It is perpendicular to dA vector by dt. But A vector has a constant length. It is not 0. Also given that dA vector by dt modulus is not equal to 0. Also given that this is not equal to 0. Therefore, A vector must be perpendicular to dA vector by dt. It must be perpendicular to dA vector by dt. Right? Must be perpendicular to dA vector. Because it is given. Very simple. A vector must be perpendicular to this. This is theorem number 3. Now I am going to give you the theorem number 4. Theorem number 4. What is the theorem number 4? If a vector T is a vector function of the scalar variable, of the scalar variable T, vector function of the scalar variable T, the necessary and sufficient condition, the necessary and the sufficient condition the necessary and sufficient condition that the necessary and sufficient condition that the vector a vector that the vector to have a constant magnitude is that sufficient condition that the vector function, even that the vector function a vector T have a constant magnitude, that the vector have a constant magnitude necessary and sufficient condition that the vector even function has a or to have a constant magnitude is a vector dot dA vector by dt equal to 0. dA vector is a vector function of the scalar variable T. If a vector has a constant magnitude, then we must have a vector dot dA vector by dt equal to 0. The necessary and sufficient condition means, if conversely, if you suppose that a vector dot dA vector by dt equal to 0, then the vector a vector T must have a constant magnitude. It's a constant magnitude. Let us try to prove this. Proof. Let us suppose that a vector has a constant magnitude, that is a vector equal to constant. C. A vector equal to A, C, equal to constant. The magnitude of this vector equal to A, equal to constant. Let us suppose this. This means now d dt of a vector now a vector square equal to a vector dot a vector. You may write like this: a vector square is equal to a vector dot a vector. This is equal to magnitude of this vector into cos 0. This is equal to a into another a into 1 equal to a square equal to constant. This is equal to constant. does A vector square equal to constant? A vector square, this is equal to constant. This means also you may write A vector dot A vector is equal to constant, which has already been written here. This means find the derivative of this. Differentiation. Differentiate this with respect to t. Differentiate this with respect to t. Differentiate this with respect to t. Constant. This implies A vector dot dA vector by dt plus J vector by dt dot A vector equal to 0. This means 2 times of A vector dot dA vector by dt equal to 0. Since A vector dot dA vector by dt equal to dA vector by dt dot A. This means A vector dot dA vector by dt, this is equal to 0. The first part has been proved. We have proved the first part. We have proved the first part. If the vector has a constant magnitude, then A vector dot dA vector by dt, then the dot product of A vector and the first derivative of this vector with respect to t is equal to 0. Conversely, suppose that therefore the condition is necessary. This is the necessary condition. It is the necessary condition. Conversely, suppose that means the sufficient condition. It will be sufficient condition. Sufficient condition. Conversely, suppose that A vector dot dA vector by dt equal to 0. This means dA vector by dt dot A vector will be equal to 0. Just add these two vectors. Therefore, A vector dot dA vector by dt plus dA vector by dt dot A vector equal to 0. This means d dt of A vector dot A vector will be equal to 0. This means A vector dot A vector equal to constant. A vector dot A vector equal to constant. This means the magnitude of this vector cos 0 equal to constant. This is equal to constant. This means that cos 0 is equal to 1. Magnitude of this vector equal to constant. Since cos 0 is equal to 1. Thus, what does it mean? Magnitude of the vector is equal to constant. This means that the magnitude of this vector equal to constant. Therefore, A vector has a constant magnitude. Therefore, A vector has a constant magnitude. A vector has a constant magnitude. It means that this is equal to constant. The modulus of A vector means magnitude of the vector A vector. This is equal to constant. We have proved theorem number 4. Has a constant magnitude. It is very easy. Now I am going to prove for the theorem number 5. Theorem number 5. If A vector is a vector function of the scalar variable then d dt of A vector cross. It is a problem, it is not a theory. This is equal to A vector cross d2A vector by dt square. You will get it like this. Proof will be completed within 2 minutes. d dt of A vector cross dA vector by dt. This is equal to A vector cross d dt of dA vector by dt plus dA vector by dt cross dA vector by dt. Derivatives of the cross product of two vectors we have already given in the last class. This is equal to A vector cross d2A vector by dt square plus, it is nothing but 0 vector, since cross product of two equal vectors is a 0 vector. Since the cross product of two equal vectors is a 0 vector, this is equal to A vector cross d2A vector by dt square. It has been proved. It is actually very easy. Now we are going to prove the theorem number 6. We are going to prove theorem number 6. Theorem number 6. The necessary and sufficient condition the necessary and sufficient condition for a vector function A vector t for a vector function this of the scalar variable t. Of the scalar variable t. Of course, a vector t, in the bracket we have written t. It means that a vector is a vector function of the scalar variable t. For a vector function of the scalar variable t to have a constant direction is that A vector cross dA vector by dt equal to 0 vector. This. Now the theorem number 6 is the necessary and sufficient condition for a vector function to have a constant direction. A vector is a magnitude as well as direction. The direction should be constant. If the direction to have a constant direction is there, the cross product should be equal to 0. Cross product of A vector and dA vector by dt should be equal to 0 vector. Proof. Before going to the necessary condition and sufficient condition, we shall prove a relation. First, we shall prove a relation. Let us suppose that the magnitude of the vector A is A. That is, vector A vector is A. That is, A vector equal to A. We have supposed this. Let A cap be a unit vector in the direction of the vector A cap be a unit vector in the direction of the vector A. Let A cap be a unit vector in the direction of the vector A. A cap be a unit vector in the direction of the vector A. Therefore, any vector, this is equal to the magnitude of this vector and unit vector in this direction. This means any vector equal to A cap. You may write like this. A vector equal to A cap. The vector equal to the magnitude of the vector into the product a unit vector and in that direction. Therefore, dA vector by dt. What will be dA vector by dt? It will be like this. A into A vector. It will be like this. This is equal to A dA cap by dt plus dA by dt A cap. Just we gave you a theorem, a formula, d dt of phi A cap. Phi is a scalar and A vector is a vector function. Vector. Then this is equal to phi dA vector by dt plus d phi by dt A vector. A vector. Phi, this is equal to scalar and A vector equal to vector. A vector equal to vector, this is equal to phi equal to scalar, this vector is equal to vector. Right? You may write like this. Therefore, A vector cross dA vector by dt, this is equal to A cap cross A dA cap by dt plus dA dt A cap. You may write like this. You may write like this. The cross product of two vectors. Now you product this one, this into this. It will be equal to A square A cap cross dA cap by dt plus this into this cross product A dA dt. It will be your scalar and it will be vector. Now, right, it will be vector. A vector, therefore you have obtained dA dt equal to A square A cap cross dA cap by dt plus A dA dt A vector cross A cap cross A cap. You may write like this also. You may write this also bracket here. Since A cross A vector cross MB vector M A cross B, you may write like this. Also M A vector cross B equal to M A cross B. Here M scalar, M is a scalar. In vector algebra you get this one, this cross this. The scalars A and A, small a, these are scalars, can be taken outside this, can be taken outside the vectors, can be taken outside the vectors following this. You may write here M A vector cross B vector also. You may write M A vector cross B vector also. This is equal to M A vector cross B vector also, like this. This formula has been applied here. This is equal to A square A cap cross dA cap by dt. Simply A vector cross dA vector by dt. Suppose this is number 1. Since A cap cross A cap equal to 0 vector, the cross product of two the cross product of two same vectors equal to 0. We have obtained this result. Now, the first I am going to prove the necessary condition. Suppose that a vector has a constant direction. Now, a cap is a unit vector in the direction of a vector. Now, a cap is a unit vector in the direction of a vector. A cap is a unit vector in the direction of a vector. Therefore, a cap has also a constant direction. But a cap has a constant magnitude. Because it is a unit vector, the magnitude is 1. It is a unit of constant magnitude. This implies that a cap is a constant vector. Simply we can say that is a constant vector. This means that the differentiation, since it is a constant vector, should be equal to 0. Since it is a constant vector, dA vector by dt is equal to 0. Therefore, 1 implies. Therefore, from 1 you will get a vector cross dA vector by dt equal to a square a vector cross 0 vector. You may write like this. This is equal to 0 vector. That is a vector cross dA vector by dt equal to 0 vector. We have proved the necessary condition. Therefore, the condition is necessary. A vector cross dA vector by dt equal to 0, provided a vector has a constant direction. If a vector has a constant direction, then the cross product of a vector and dA vector by dt should be equal to a 0 vector. Now, necessary condition has been proved. We have now we are going to prove the sufficient condition. Now I am going to prove the sufficient condition. Conversely, suppose that a vector cross dA vector by dt equal to 0 vector. Therefore, from 1 implies means from 1 you will get this is equal to 0 a square a cap cross dA vector by dt equal to 0 vector. This means a cap cross dA cap by dt should be equal to 0 vector. Suppose this is number 2. Suppose this is number 2. Now, a cap is a unit vector, means it has a constant magnitude. A cap is a unit vector. This means a cap has a constant magnitude. A cap has a constant magnitude. This means by theorem 4 you will get the dot product of this is equal to 0. From 2 and 3 you know this, the cross product of a cap and dA cap by dt is 0 vector. Also The dot product of a cap and b a cap by dt is also 0. What does it mean? What does it mean? Just imagine, what does it mean? This means that from 2 and 3, from 2 and 3, a cap is a unit vector, constant vector. If this is equal to 0, 3 possibilities are there. Magnitude of this is equal to 0, magnitude of this is equal to 0, or this is perpendicular to this. At the same time, it is the cross product is also 0. How can it be perpendicular? Only from 2 and 3, we must have only one possibility: dA cap by dt equal to 0. dA cap by dt equal to 0 vector. This means a cap is a constant vector. This means that a cap is a constant vector. Constant vector. This means that a cap is a constant vector. This means that a cap has a constant magnitude as well as constant direction. This means that a cap has a constant magnitude as well as constant direction. A cap has a constant magnitude as well as constant direction. Constant magnitude as well as constant direction. This means, but a cap is a unit vector in the direction of a vector. Therefore, a vector has a constant direction as well as constant direction. Constant direction. A cap is a unit vector in the direction of a cap. A cap has a constant magnitude as well as a constant direction. A cap has a constant direction, but a cap is a unit vector in the direction of a vector. Therefore, a vector has a constant direction. This proves the theorem. This proves the theorem. Let us take some simple problem. Perhaps you have understood everything. Let me write the problem. Let us try to solve these two problems. Number one. R vector equal to cos nt I cap plus sin nt j cap. This means dr vector by dt equal to minus m sin nt I cap plus m cos nt j cap. You will get like this. Therefore, R vector cross dr vector by dt. The cross product you may write here I cap, j cap and k cap, and you write here cos nt, sin nt 0, minus n sin nt, n cos nt again 0. This is equal to this into this minus this into this. Sin nt 0 minus n cos nt 0. You may write use this bracket I cap plus for j cap this minus n sin nt 0 minus cos nt 0 j cap plus this into this cos nt into n cos nt minus n sin nt into k cap. K cap. 0, 0, this is equal to 0 I cap plus 0 j cap. It will be n into minus minus plus n, common. Cos square nt plus sin square nt. K cap. Yes, k cap. This is equal to n. It is 1. This is equal to 1. Therefore, n k cap. N k cap. N into this is k cap. Therefore, 1 has been proved. It is very easy. 1 has been proved. We have proved this one. Now, let us try to prove number. Let us try to solve the number 2. Solve the number 2. We have proved number 1. Now, I am going to solve number 2. Now see, R vector is equal to A cos n t, A cos t, I cap plus A sin t, j cap plus A t tan alpha, k cap. We are to find dr bar by dt, d2 r bar by dt square, also dq bar by dt cube. dr bar by dt equal to, with respect to t, minus a sin t I cap plus a cos t j cap, with respect to t differentiation, a tan alpha k cap. It will be like this. d2 r bar by dt square will be equal to minus a cos t I cap minus a sin t j cap. It will be 0. 0. All terms are constant, 0. d cube r bar by dt cube. This is equal to d cube r bar by dt cube will be equal to this t. It will be a sin t I cap plus a cos t j cap. A cos t j cap, simply. Now this cross this, this cross this. Therefore, d r bar by dt cross d2 r bar by dt square equal to the determinant I cap j cap k cap. d r bar by dt, write minus a sin t, write a cos t, write a tan alpha, and yes, write minus a cos t, right, minus a sin t, and also 0. And also 0. This is equal to, from this I am writing here. From this I am writing here. I cap this into this minus this into this. This into this 0 minus 0 plus. It will be a square tan alpha sin t. A square sin tan alpha sin t I cap. I cap. For j cap, this into this minus a square tan alpha cos t. This into this minus 0. Minus a square. Minus a square tan alpha cos t. This into this plus 0. J cap. J cap. Also, this into this a square sin square t. A square sin square t minus minus plus a square cos square t. Cos square t. From this, I am writing here. This is equal to a square tan alpha sin t I cap minus a square tan alpha cos t j cap plus a square k cap. Simply. Now you have to find the determinant. Therefore, the magnitude of this, the magnitude of this equal to root of r a square tan alpha sin t whole square plus minus a square tan alpha cos t whole square plus a square whole square plus a square whole square. This is equal to a to the power 4, a to the power 4, a to the power 4. A square can be taken outside the root of r sine. Tan square alpha sin square t. Tan square alpha sin square t plus tan square alpha cos square t plus 1. It is nothing but 1. It is nothing but 1. Now, nothing but 1. Now, let me write like this. Yeah. This is equal to a square root of r tan square alpha sin square t plus cos square t plus 1. This is equal to a square root of r tan square alpha plus 1 equal to a square sec alpha. This is the answer of this. Number 1. This is the answer of number 1. A square sec alpha. A square sec alpha is equal to this. Now we are going to find the second one. You see, it is nothing but the scalar triple product of 3 vectors. Scalar triple product of 3 vectors will be equal to dr bar by dt dot this into this cross this. And in a scalar triple product, position of dot and cross can be interchanged. In a scalar triple product, position of dot and cross can be interchanged. Therefore, position of dot and cross can be interchanged. Oh, I am very sorry. No, take it. Second part. d r bar by dt, d2 r bar by dt square, d cube r bar by dt cube. The scalar triple product of this. This is equal to d r bar by dt cross d2 r bar by dt square dot d cube r bar by dt cube. You may write in this way. We have already calculated this. What is this? Equal to this one. This is equal to a square tan alpha sin t I cap minus a square tan alpha cos t j cap plus a square into k cap. This dot into this a sin t I cap plus a cos t j cap dot a sin t I cap plus a cos t j cap dot this one. We have written this one. This is equal to this into this a square tan alpha a cube tan alpha. You may write like this: a cube tan alpha sin square t it should have been plus, I think. A cube tan alpha cos square t. minus a sin t plus a cos t. Minus a sin t plus a cos t. Minus a sin t plus a cos t. Minus a cos t minus a sin t. Now, okay, well, I want to check you one thing. R vector is equal to, you have got here dr bar by dt, just 1 minute, dr bar by dt minus a sin t I cap plus a cos t j cap plus a tan alpha k cap, a tan alpha k cap, d2 r vector by dt square, d2 r vector by dt square is equal to minus a cos t I cap minus a sin t j cap plus 0. You will get this one. And d cube, dt cube equal to, it will be plus a sin t I cap minus a cos t j cap, minus a cos t j cap. I am very sorry that earlier d cube r bar by dt cube was written as a sin t I cap plus a cos t. It is not plus, it is minus a cos t. It will be minus a cos t I cap. Just correct it. Clear? Just a simple mistake was there. Just it should have been minus a cos t. You see here dot product of this into this, a cube tan alpha sin square t plus a cube again tan alpha cos square t plus a square into 0. You will get this, a square into 0. This is equal to a cube tan alpha sin square t plus cos square t. This is equal to a cube tan alpha. Answer is this. Answer. Just notice this term. D cube r bar by dt cube. It should have been a sin t I cap minus a cos t j cap. Earlier we wrote it as plus a cos t j cap. It is not plus a cos t. It should have been minus a cos t j cap. Just one simple mistake was there. Just we have corrected this. I think there will be no problem. Perhaps you have enjoyed the class. Thanks for attending the class. Thank you very much.